So finally, we can be done with resolution today. So remember, this has been a long saga to get here, but we had, going back a couple of lectures, the idea of proof by contradiction. So we negate the thing, we convert it to clauses. I mentioned the resolution idea. Then in the last lecture, we looked at unification, which is necessary in order to handle the terms when we want to when we need terms to plug in for variables in order to prove things. And I sketched the claim, this theorem, Herbrand's theorem, that if there exists a contradiction in your set of clauses, then it can actually be exhibited in a finite way, which of course is one of those annoying restrictions computers have. So now we can look at the resolution as it properly is. Oh, by the way, why on earth does it say binary? Kind of one of many historical legacies here. There were loads of experiments with different kinds of resolution, and there was a thing where they had like a whole bunch of things done at the same time. I think they called it hyper-resolution, where you were basically like a string of these binary steps. Binary, I merely mean it's taking two operands. So there was a craze at one point for doing not just two, but like n operands and kind of cascading them down. No one does that anymore, so the word binary here is obsolete. So we're always here interested in just the two premises. Remember, these are clauses which represent disjunctions of literals. And in the original, when I showed you what resolution looks like in propositional logic, this thing here was not B. No, it's exactly the same as B, only negated. And the only thing we're doing now is we are using unification to say, well, they don't have to be identical anymore, as long as you can make them identical by unifying them. So really a very simple idea. If B is unifiable with D, then we can form a conclusion by, now, if you remember from when I gave you the propositional version of this, I said you take all the other literals and you just stuff them there together into a big clause. And the only difference now is we unified B and D by this substitution sigma. And remember, when I told you about unification last time, I said we don't just want to make the terms the same. You need to remember how you did it. Because, if you set x to 3 or whatever, there will be other x's in other places, and you need to set all of them to 3. So that's what I mean by this substitution sigma. So we did something to make these two the same, and that something has to be done to everything else as well. In a computer, this turns out to be trivial because you do everything with pointers. So you set the pointer to 3, and then all the uses of the pointer always automatically see the 3, and there's really no work involved. Okay. What do I mean by most general unifier? Actually, this rule is sound for any unifier, because whenever B substituted with sigma equals D substituted with sigma, whenever they're equal, this thing makes sense. But of course, what is the best way to do it? The idea of a most general unifier is one of those things that doing it any other way would be stupid. The idea is, literally the most general possible thing. So I have these two terms here. So fxy, x and y are variables. Faz, a, and a is a constant, z is a variable. So clearly I need to set x to a, right? No alternative. Now y and z need to be the same thing. Now you might ask, actually, does it matter whether I set y to z or z to y? And the answer is it doesn't really. Okay, strictly speaking, they are two distinct unifiers, but it's still a variable. It doesn't make any difference at all in terms of anything important. However, what happens if you set y and z to 77? That would just be stupid, right? That's an example of a unifier that is not most general. So a most general unifier is simply one that has variables everywhere it can. And I think there's a formal definition which basically says it's most general if you can obtain any other unifier by a further substitution. You don't need to worry about that. You see, if you do unification in the very naive way I sketched in the last lecture, you will always get a most general unifier. You don't have to do anything special to get a most general unifier. Indeed, you have to do something special and kind of dumb to get one that isn't most general. Now, I'm going to say this again. I'm saying it because it's really heartbreaking to mark exam questions. Why did they do that? They were almost there, and yet... So, and especially... Now, I didn't stress it so much. The treatment of unification goes by a bit quicker than it did in the past for my course, but you also get unification again in the Prolog course, and they will tell you very strictly about this so-called occurs check, which basically means if you are unifying, you want to unify x here with some term t, and it turns out that t is something with an x in it, then it's not allowed. So you cannot replace x by a thing containing x because that would make a loop. And that's true. You cannot, you must make this check. So when you want to update the variable x with some term, you must indeed check whether there's an x there. And if there is an x there, and I'm tempted to cross it out, but you're copying it, so just, you can't do it, right? Like, boo. I'll just express, I don't have another color pen, you see. Anyway, so then some students come along, they see this clause here and that clause here, and they think, oh, I can't do a resolution because of the occurs check. Why are they wrong? They are wrong because these variables are in different scopes, which means you have the right to rename these variables. And in fact, if you write code for a resolution theorem prover, one of the stages in the resolution theorem prover is, you pick this clause, and then you pick that clause, and then you rename the variables, which typically you do, not in any fancy way, but you keep some big counter there, some offset. You add, because your variable names are just numbers, right, in a computer. Just add some fixed number to the variables in this clause to make them bigger than those so that they're all distinct to begin with. Now, you may imagine, oh, well, the occurs check can never be relevant to resolution because of this renaming. But that's also wrong. In fact, if you go back to the lecture before last, if you remember the example with the quantifiers, you will see that, in fact, I was careful to make the variables distinct in that last example, and yet there is still an occurs check that happens. Okay, resolution is not enough. Why is that? It's because we're trying to get the empty clause, and yet we keep joining these two rules together. Okay, we cancel out two literals, but we add in all the rest. It looks like things are getting longer and longer and longer, so how do we ever get to the empty clause? Well, sometimes, just very rarely, a lucky thing happens. So these things are sets, so if you get a couple of p's in there, they will collapse down. That's helpful. But that's not enough. You need to make it this. You need to force this collapsing to happen. So we need a second inference rule for resolution. So maybe to repeat myself, resolution is a formal calculus, just like, let's say, the sequent calculus was a formal calculus, and that Hilbert system was a formal calculus. Each one of these has its inference rule. So in the case of this one, we have two inference rules. One is the resolution on the first slide, and the second one is this thing here. And what this says is, if you've got a clause, and if you find some literals more than one, so some b1 up to bk, and why did I never write clearly k greater than 1 here? Otherwise, there's nothing to do. And if you can make them all the same by unifying them, then you can collapse them down. So I find a unifier of all those literals, I apply it, and I now make a new clause. This clause will typically look less general than what we started with, because typically, unification will replace variables by constants or whatever, but it will be a shorter clause. So we'll see, I have some examples, we'll see how this helps us out. Now, it turns out, and God knows I'm not going to prove, these completeness proofs are really tricky. You can prove that the two rules together, resolution plus factoring, is a complete proof system, and that means you're guaranteed to get a proof eventually. By eventually, you should be thinking of kind of cosmological time spans here, and cosmological amounts of memory. So, just as a little remark, if your theorem prover has taken more than 10 seconds, it's probably not going to prove it. There are exceptions. Occasionally you get a proof after like a minute or two, but that's rare. So you can just kill it at that point. Okay, I have an example here. Even in the tricky old days when I tried to do some proofs right in front of you, I would not tackle this because it's kind of hellish. And if I'm ever cruel enough, or if anyone is ever cruel enough to ask you to turn this thing into clauses, it's really very tricky because there's actually two ways of unfolding if and only if, and you need to know which one to choose in order to have the least work to do. And that's why we let computers convert things to clauses. But this is a theorem, so we negate it, we go through all the rigmarole, and we get just two clauses. Now, a little tip for exam questions, and if you go back, you will see this. Of course, there are lots of resolution questions on past exam questions, and with some of them, you have this situation where there are no unit clauses. You remember what a unit clause is, right? That's with a single literal. This has two literals. So, you already know either some kind of collapsing will happen or you will not find a proof at all. And that's because with two literals, if you resolve, and they all have two literals, you're always going to get at least two literals in the conclusion. So what about here? Well, here we see two opportunities for factoring. See, these two literals are the same, right? It's very clear that if I plug in A instead of Y, it becomes a unit clause. Here, the same thing. If I plug in A instead of Y, and by the way, these Y's again have separate scope, although it turns out we're plugging in the same thing for them anyway. But both of these can be factorized, and then it suddenly becomes trivial. Yeah, so when I'm in a mean mood on setting exam questions, I make sure to set a thing where you have to use factoring, and then if you don't know about factoring, then you'll never prove it, or maybe you give me a bogus proof, which is even worse. Okay. Here's another one. This one at least is a little more intuitive. What have we got here? We are claiming if that exists and that exists, then that exists, where what is it? For some x, p implies qx. For some x, qx implies p. Then we are claiming that for some x, I see you have the if and only if. Well, one thing I can say without even looking at this is I think I will just try, just to show you I'm not completely brain dead. see if I can convert this into clauses without looking at the rest. Remember, I told you, if you are asked to prove a thing with an implies in it, then you can get the thing to the left of the arrow will be positive even after negation, so you can convert them straight to clauses. And this one looks like the clause not P, Q of A. There I have skolemized that. This one looks like, again, skolemizing, I have to be not A, but you have to choose something different. A big boo-boo if you don't. Not Q of B, comma, P. Oh dear, this one is harder. That will turn into a for all. And I think, though, this will be a negated if and only if. My brain is not powerful enough this morning to deal with it. Did I get this right? Is there a not P and Q of A? It's there. Is there a Q of A, not Q of B and P? Yes, it's there. I know I would have gone wrong. Here, this, you have to negate this. It would be for all x, and actually what you would do is that would be for all x, and to negate an if and only if, it's enough to negate either side. So I could turn this into, for example, not P implies QX, and QX implies not P. And that's how you, yes, so not P implies QX is actually that one there. And QX implies not P is that one there. Okay. Now, again, we see that there are no unit clauses. They all have two literals. And I will need to do something in order to get a proof out. Now, I'm not sure that factoring is strictly necessary here because we've got these P's, which they're propositional already, right? They have no arguments. And I can easily imagine that if I resolve some things, that I will get two P's there quite quickly. So let's say, what can I do? I have QX here. I have not QB. That is going to tell me P, right? So the P, comma, P collapsed down to P, and I didn't even need to use factoring. What about over here? I have not QA. I have QA and not QX. This is going to give me a not P. And from those, I indeed get a contradiction. Does that agree with this? I see I called that factoring. It's not really factoring. It kind of amounts to the same thing, but strictly speaking, it's just because they're sets. Okay. I hope that made sense. Just a little aside. I give you baby examples, not because you're babies, but because slides are very small. But if you're really using resolution, and typically you'll choose a problem in, I don't know, group theory or something, and then you have to include files of group theory axioms and God knows what else, and pretty soon your resolution prover has been given 300 axioms, most of which are completely irrelevant. And then, you run it. It runs, as I say, maybe for 5 seconds. A proof comes out, and it has used like 5 of your axioms, and all the rest are junk. So there's an engineering problem in terms of making the thing run fast enough that it can find the 5 things that are relevant and get the contradiction out. And, of course, wasting lots of memory and all the other ones and all the loads and loads of other resolution steps that don't lead anywhere. And in fact, if you try things yourself on paper, you will yourself do loads and loads of useless resolution steps as well. So I'm not going to say a lot about how this is done. If any of you want to do a resolution theorem prover as a Part 2 project, that's great. It won't be an easy project. It's probably easier than writing a chess program, but they're kind of... Anyway, as I said, there's a vast amount of special tricks that can be used here to help us out. One little other corner. So you can't express much without the equals sign. The trouble is, equality is a pain. Now, you may have noticed in the sequent calculus, I didn't mention equality at all. And there is really no nice way of doing equality in a sequent calculus prover. In resolution there is, but it's not nice enough to really teach you about, but I can at least mention two things. First of all, we can do it by brute force because we have a complete calculus. So if you just throw in the theory of the equality symbol, the first order theory of the equality symbol, it will work. Now you need to have the equality theory, which means things like x equals x, but you also need to throw in these kinds of axioms. So for every function f, and I am assuming here a one-argument function to keep it simple, this very obvious property that if x is equal to y, then f of x is equal to y. And this is a similar substitution property for the predicate symbols. If you throw all of those in, then in theory it can prove all your equalities and you will have a complete calculus for first order logic with equality. In practice it sucks. So you need to use something like this, and I'm not going to explain it in any detail because we're not going to use it. Just to tell you what it is, for this we are extending our calculus with a third inference rule. And if you look at it, you can kind of figure out that it's something like resolution. So you've got, in particular, you've got these side literals, the A's and the C's, which end up in the conclusion exactly like in resolution. But what we're doing instead, we have a literal here, and we have an equality there, and we're unifying this term t here, which is equal to u, unify that with some subterm of this other literal, and then you see in the conclusion we've replaced it by u. So we've done a kind of substitution step. Getting that to work is hard, and I don't actually ask you to do a thing like that. So I'm just showing you that just for your own intellectual enlightenment. And now we have a very important side note here. These are based on real-world experience, you know. The guy who draws these, he gets letters from people who work for companies. And he actually mentioned a story where a company where I think all the managers had offices with windows, and the engineers had these kind of cloth-lined cubicles. And they needed an office but for an engineer, and they had only a managerial office, so they actually put a cubicle inside so he couldn't look out the window. That's the kind of thing they do. Anyway, so I need to make a link to Prolog. I'm not going to teach you Prolog as a programming language here. That's for the other course, but I'm just trying to show you like where Prolog came from. So and repeating myself again, they really were trying in the 70s to think by theorem proving, and they were failing. And in general, they kind of got the idea that resolution wasn't good for much, and it was one of these overhyped things that was a complete waste of time. And as they were trying to improve the performance of resolution, because they seemed to have a really big search space, wasted lots of memory, and did very little that was of any interest to anybody, they started saying, what if we restrict the resolution rule in this way or in that way? And as I think I hinted a while back, we now have a very powerful way of restricting the resolution rule called superposition. And this is the key to all the really powerful theorem provers you can download today. But they hadn't thought of it then. So the ideas they had were very, very much simpler. What they kind of arrived at was a special restricted form of clause called a horn clause, and a very deterministic approach to looking for possible unifications, a kind of starting to impose left to right behavior on this. And at some point they noticed, hey, this is behaving like code. And that's when they made the transition from proving theorems to executable code. Now, the reason people got so crazy about Prolog, there were two reasons, actually. I guess Lisp is nothing but a distant memory now. I mean, how is it that vinyl records are still with us and Lisp is gone? And people managed to convince you that vinyl records sound better than modern things, which I doubt if that stands up to kind of objective measurement. However, Lisp is quite dead, but the AI world at the time, at the 70s, was quite wedded to this Lisp language, which one particular feature it had was that its core data structure was also directly executable, so that the thing that it manipulated was also the thing it executed. And in Prolog, they suddenly had another language with that property, so that the clause language that is executed in Prolog is also a data structure in Prolog. So that turned on a bunch of people. As I say, a successor to Lisp, though it didn't happen that way. But also the backtracking that naturally arose from this interpretation of theorem proving was a thing you couldn't do in Lisp. Now, I'm sorry to say that in order to turn this into a proper programming language, they added a whole bunch of junk to it, which is actually what they did to Lisp as well. So that, because after all, you cannot print in logic, and you can't add a couple of floating point numbers in logic either. So they threw in all those things to make a real programming language. Oh, and by the way, these are the names of the guys who did it. And that's where Prolog came from. Let me just show you what a Prolog clause looks like. So you already know what a clause is, but in general, a clause can have any length, of course, and we have always regarded a clause as a set, so the order of the literals didn't matter, and it could have any number of positive or negative literals, or both, of course. Now we say, only one positive literal allowed. And in fact, okay, horn clauses have at most one positive literal, but strictly speaking, I'm sorry for all the jargon, I didn't invent it. They're interested in so-called definite clauses, which have exactly one positive literal, and they are written like this. So logically, these are the same clauses as we already know and love, but we are now writing them like this. We are now starting to regard the order as significant, so the A's are negative, the B is positive, and suddenly we're saying, this is expressing a line of a subroutine, and it is saying, to do B, do A1 up to AM. That is, of course, the procedural interpretation. The logical interpretation remains as before, that is, B will be true provided A1 up to AM are true. Now, I mentioned there can be a clause, but only one, that has no positive literal at all. It's written like this. It's called the goal clause, so you have just one of them. And if you like, the purpose of the goal clause is to store all the tasks you've got to do. You put them in like this. They will be executed in order, starting at A1, and finally, after AM is finished, then the program terminates. And this is effectively nothing but a stack. Now, we are still resolving. Now, remember what we do in resolution. We resolve a positive literal with a negative literal. Here, the negative literal will be this one here. That is the first literal in the goal clause. The positive literals will be taken from, now I've written only one here, but in general there could be any number of definite clauses. You'll match one of these to that one there, and if there is a match, then those things will be shoved in, and so on. I will give you some examples, and I hope it will be clear. So, Prolog, when a Prolog program runs, or at least a pure Prolog program, so let us forget for the moment all the crap they added to Prolog to add floating point numbers and print and all those other things. It is just doing resolution, but it's doing resolution in this restricted way called linear resolution. You'll see why it's linear, I think, when I give you an example, because it simply means you're going in a straight line. You have your goal clause, and every resolution step gives you a new goal clause, new goal clause, new goal clause, down it goes. So you have a straight line of goal clauses. When termination is finished, it's because there are no goals left, which is, of course, the empty clause, right? So you kind of proved a theorem that, and it's kind of bizarre to think that giving your thing a task, a list of tasks to do, you run those tasks kind of logically by deriving a contradiction. But that's how it works. So, as I just said, you have your goal clause, and then you pick a program clause that matches it. This picking, of course, is done deterministically by the machine itself. And the new goals from the program clause are stuck in front of the goal clause, giving us a stack-like behavior. And everything is done left to right. I hope they still teach you what depth-first search is in the first year. So depth-first search is the usual idea of backtracking where you try a thing. If it fails, you go back to the last choice point, try a different thing, try a different thing. This comes out very naturally from, well, I guess the logical interpretation of these, of the idea that we are still trying to prove theorems, but in this very restricted way. So if one goal clause matches but leads to a dead end, you might find another matching program clause, try that one, and so on. And it very nicely generates this backtracking search. The other thing now I mentioned, I think that normal resolution to prove theorems works by saturation. That is, you start with some clauses, you do loads of resolution steps until either you get a contradiction or you run out of memory. Prolog is not saturation. So as I said, you have your goal clause, which keeps getting transformed. You have your program clauses, and they stay fixed, and there are no other clauses. Right? It's not just throwing out clauses willy-nilly like normal resolution. The outcome of any resolution step is a new goal clause. If it reaches a dead end, it unwinds, throws everything away, then tries other things and makes new goal clauses. So it's using much less memory. What about the occurs check? The problem with the occurs check, so I drew that nice picture. I don't know if I can find it, but remember, whenever you are trying to update some variable x with some term, in theory, you're walking through that term to check whether there are any x's in it. But think now, unification is now the way we pass parameters in Prolog. So these predicate symbols are not really logical anymore. There are procedures, and unification is passing information into these procedures. Clearly, what you can't be doing is walking over your arguments of your procedures every time you call a thing, because execution will take forever. So they just don't do it. So they do a naive unification, which then if you're not doing the checking, you're just shoving the thing in. If it makes a cyclic data structure, that's too bad for you. But that's programming, right? These days, a Prolog system will offer you as an option a kind of unified predicate that does it properly. Now, there's a funny thing here. These databases of families are the classic Prolog application. And I see that Prince Andrew got his name taken off many things, but he is still on these slides, which I made a long time ago. Prolog is very good at dealing with family relationships. So you see, these are 6 definite clauses. In Prolog jargon, they're called facts because they're unconditional. These are all unit clauses. And we have 2 more definite clauses. Say this one defining the grandparent relation, and that one defining the cousin relation. And I hope you can see that you're able to express, I mean, certainly some people say, well, this is kind of like a database, and if you allow not 6 things, but, 100,000, it could even be a big database, and it looked a little bit like the relational databases that were totally like an exciting new development in the 70s. The bee's knees, as they would call them then. But these last 2 clauses go beyond any normal database. That's why you sometimes heard the term deductive database, because in the same language, you can express derived facts about, derived information about your gigantic set of facts here. Now, the way this is going to work will seem kind of cool because, as I said, kind of intuitively, these last 2 are procedures, and it kind of says if you want to show X as the grandparent of Z, you have to show those 2 things. And yet this is not like writing code in C or something, because I've simply said for X to be grandparent of Z, X needs to be parent of some Y, Y parent of some Z, and you see Y was not mentioned over there. So Y is simply being thrown in as a thing that is now something you have to deal with. And so we have this ability to call up the existence of things that you hadn't imagined when you asked this grandparent relation in the first place, and yet it will be dealt with very nicely. Cousin is similar, so you see X and Y are cousins if they have a common grandparent, Z. So now, when I go through an execution, how did I do this? Can I do this? Maybe it's stupid to try, but are you even plugged in? We will see. Woohoo! It's even plugged in with the visualizer port, whereas that thing is plugged into the VGA port. So, which proves there is a God. Okay. So we begin. So our goal clause says cousin XY. So execution comes down here. None of those match, so they're tried, of course, from top to bottom, but none of them match, and of course a good fast Prolog system will not try from top to bottom because it will have fancy data structures and it will zoom right in on the matching thing directly. Anyway, the only thing that matches is cousin XY, and it will make these 2 sub-goals, these grand sub-goals, which will replace the original goal. Remember, this is our goal clause. Now it's a bit longer. Why does it say Z1? Well, I told you, whenever you do a resolution, you need to rename the variables in one of the clauses, and that is what happened here. So whenever you call this, you see, if you didn't rename these variables, we would be using X and Y, and then we would have the same Z every time, which meant we couldn't ask for 2 cousin relationships unless they happened to have the same grandparent involved in all of them, and that clearly doesn't make any sense. I mean, it's a bit like Fortran. None of you know Fortran from way back not even Fortran today, but back when things were really allocated in static blocks of memory back in the 60s. Prolog isn't like that. So every time we call this, we get fresh variables. And all that involves is for the system to rename the variables before it does the resolution, which is why the variable we get here is called Z1. Now this will be treated from left to right, so we will look at this literal, Z1 and X, and look for a thing that matches. The only thing that can match is this grandparent clause. And again, this is just a normal resolution. And these two parent literals will be substituted, as you can see, for the first literal there. And those are now Y2, because again, we have renamed the variables. We keep a counter somewhere that we use to rename so that there can never be a clash of variables when we generate a new clause. Now what do we do? Now we have these parent, and remember these are negative literals because they're in the goal clause. So this is a negative parent literal. These are positive parent literals. And of course, it will pick up the first one, parent Elizabeth Charles. Now, what happened here? This maybe is a little confusing. Because that has no sub-goals, right, this is just a fact. It's unconditional. So this literal simply disappears. But it had the effect of, so you see, Z1 became Elizabeth and Y2 became Charles. Now, as I told you, when you do a unification, you need to apply it elsewhere. So Z1 became Elizabeth, which is why we get Elizabeth there. Y2 became Charles, and that's why we get Charles there. And I hope you can see how cool this is, that unification is building up the things we need to do directly. Now, parent Charles X, it will go past those and it will pick up William as the first possibility. And yes, the Prolog system actually will notice when a variable mentioned in the original goal gets updated, because it needs to give you that. So if you've actually tried playing with Prolog and you actually run this code, it will tell you what the matches were. So it will say X can be William. Oh, and I forgot to mention, so this original goal, cousin XY, you see, I could have put in particular names. I could have put in something like cousin Elizabeth Beatrice, and it would have failed. And it would have done the test, and it would have failed because they don't have a common grandparent. I could have put in, I don't know, cousin Henry, this is Prince Harry, of course. I could have put in cousin Henry Eugenia, and it would have succeeded and said true. So it can test the cousin relation. But it can do more, because if I put in variables, it can enumerate cousin pairs, and that's even cooler. It's one of the things that really got people excited about Prolog, because it could actually generate solutions. So anyway, William comes out. We still have a grandparent literal to solve. We go through, again, we have only one clause can be matched for doing grandparents, which is this one here that substitutes two parents. So it says, okay, if you want Elizabeth to be grandparent of Y, you need some Y5. Elizabeth will be the parent of that, and that Y5 is the parent of Y. Now here, actually, I cheated. You see, it's a sorry thing about the way this works. What it would have done, it would have picked up Charles again, and when I did the next one, it would have picked up William again, and it would have said William is the cousin of William, And that is actually the first. If you run this, and you can type that into a Prolog system and run it, and indeed you will get William as the first cousin pair. And that's because it thinks you're your own cousin. One could alter the program, I guess, to prevent that. How exactly? Because it also says your brothers are cousins, and that's not what people really want. But the thing is, though, with the way Prolog works, you can force a backtrack. So at the top level, in fact, you can type a semicolon, which basically says, go on, give me another one. We'll then go back and make another choice, and you can keep forcing it to backtrack. So I can keep forcing it until eventually it rejects Charles and switches to Andrew. And then when I unify Andrew, parent Andrew, there are two possibilities. The first one it will pick up is Beatrice. And then there'll be no goals left, which is formally the empty clause. So if you like, the original goal was effectively saying there are no cousins. So it's kind of denying the existence of an x and y. So it's kind of saying, I guess, for all xy, not cousin xy. And when we get the contradiction, it's saying, oh, you're wrong. Counterexample, William and Beatrice. So that's kind of intuitively what's happening there. Anyway, I hope it's clear why it's called linear resolution. And of course, you will learn a lot more about Prolog in the other course. I want to say a few more things quickly. So what I just showed you is not just a toy. And a lot of people really liked using Prolog for that sort of thing. That is, when you have a lot of facts and then some kind of meta-reasoning about them. But also, probably this is obsolete by now, but in the 70s it was noticed that you could express parsers very easily in Prolog, and you could also hook some semantics also done as Prolog code in with these parsers. So these so-called definite clause grammars caused a lot of excitement. And maybe another thing was that people were already interested in backtracking. So it was already understood that backtracking was a very basic kind of planning for AI. So as I said, people went mad, especially when the Japanese government announced they were going to put a lot of money into Prolog, because back then everybody was terrified of Japan. So then the British government said, we're going to spend a lot of money on Prolog as well. And as what usually happens when they spend a lot of money at once, loads of it was wasted. Right. You want to... Just to learn what suffering is ahead for you. Or you could go into academia. Very briefly, so this is not really examinable, but I just want to mention, so Prolog originated in ideas to make resolution run faster. And then it was turned into this weird programming language to write code in. And they even made, with the help of all that money I mentioned, very high performance architectures for running Prolog code. And then the theorem proving guy said, this isn't fair, we want to prove theorems. So somebody thought of a way that you could kind of hack theorem proving so that it looked like Prolog, and then run it on a Prolog kind of, one of these optimized Prolog systems that people were building. So what they did, now remember, now we are trying to prove theorems. We have clauses like these. We're going to pretend they are Prolog clauses. And the way we're going to do this, you see, because this is a set and there is no particular order on these literals, we're going to impose an order on them. So we're going to say, well, we could write it as a Prolog clause by selecting A1, I mean, as the head. But then we're not sure that is the right one to put in the head, so we can try A2. In fact, we'll try all of them. So replace this one normal theorem proving type clause by M kind of pseudo Prolog clauses. Put in a couple of other hacks, and then it turns out you can throw this at a Prolog engine, and suddenly it will be running these pseudo programs and actually has the effect of proving theorems with a very high performance compared with the things they could build at the time. So that was cool. Since then, as I've mentioned, people have come up with much more sophisticated ways to control the search space in theorem proving, so we don't need to do that kind of thing anymore. Now, I have this slide here of all these different things, but really the main ones are the ones at the bottom. So the E-prover, Spaß, that's German for fun, by the way, and Vampire. I think Vampire can be a bit tricky to download the sources for, but certainly the other two, if you have time to waste, download them. It doesn't matter, I think, if Mac, Linux, Windows. Windows is probably your worst option, but I think you can get them running on any of them. Have fun, and you will see you can prove some much, much bigger examples than you could ever see in this course. So that's it for now.